Earlier, we saw how the training loop works. You make a guess, you measure how accurate that guess is by calculating its loss. And then you use that data to make another guess, with the next guess being a little better, usually than the current one. The idea is that the smaller the loss, the more accurate your guess is. So now we'll explore how you minimize your loss. So let's look at how gradients and derivatives can help us understand how to minimize loss. In other words, how an optimizer function works. Let's plot our loss function. You'll remember, we were squaring values to remove negative. So our function is a square of something. Square functions have a parabolic shape like this one. If we want to know the minimum of a loss function, we just look at the bottom of the parabola. Whenever the parameters that make up this function and whenever this would be plotted on a chart, we know that the minimum is at the bottom. So we have made a guess as to what the parameters of our equation would be. Say we started with y equals 10x plus 10, for example, and calculated the loss for the data in our equation. We know it would be very high and far from the minimum. Maybe it would look a little like this. Now it gets interesting. And here's why we generally see a lot of math and calculus in machine learning. If you differentiate the values with respect to the loss function, you get a gradient. The nice thing about having a gradient is that you can use it to determine the direction towards the bottom. You have no idea how far it is to the bottom, but at least you know the right way. It's like a ball on a slope. Gravity will give you the direction to the bottom of the slope, but you don't know how far it is. So if you want to go towards the bottom, you can take a step in that direction. You know what that direction is, and you can pick a step size. The step size is often called the learning rate. So given a direction from the gradient, and a step size from the learning rate, you can now safely take a step towards the minimum. And you'll end up here. You're closer to the bottom. You still don't know how far it is, but you're closer. So you can repeat the process. By differentiating again, you can get the gradient. And from the gradient, you can understand the direction towards the bottom. And then you can move again in that direction of the gradient. And we'll end up over here. Repeat the process again, and you could end up over here. You're getting closer. Another step, and you'll be here, closer still. So the next step we could have given us an overshoot across the bottom, and we end up here because of our step size. But that's okay, because when we differentiate this spot, we'll have a new gradient pointing towards the bottom. And so we might end up here and overshoot again, going backwards. And after a few steps, we could find ourselves oscillating over and back, and we're gradually approaching the minimum. It's important to choose a good learning rate, or we would oscillate forever. Or indeed, an advanced technique is to adjust the learning rate on the fly. It might be good to have it bigger when we are further up the curve and gradually reduce its steps by step as we get to the bottom quicker. To illustrate, choosing a learning rate wisely is important. If it's too large, we could overshoot like this and overshoot on the way back. And then overshoot again like this, gradually, never actually reaching the minimum. Or if the learning rate is too small, then it might take a long time to reach the minimum. A long, long time as we get to the next step, closer, but it takes too long, right? So tiny increments will get you there, but it's not the most efficient way. And so now it's your turn. You'll try a Colab first that does this gradient descent using TensorFlow, and you'll see how it figures out the minimum loss.